So now let's think about how we can interpret these beta coefficients. So let's discuss how we can interpret these beta coefficients. So we have our kind of beta coefficient regression. So zy equals, we wrote it back as b hat 1 times zx1, right? This is kind of the z score for x1. This is kind of the z score for xy. And we have all these different coefficients, these parameters. I'll put a k on that. Z, xk. We have this other error term here. So I should put an I on that. We can put an I on this, and then this, and on this. And let's think about how now we'd interpret these parameters if we were to run a regression with beta coefficients. So the interpretation is now the following. And we're going to keep it kind of general here. Let's look at a specific example in a couple seconds, so we're actually looking at actual variables. So we can think about how to interpret an actual situation. So how to interpret this kind of general format is if x1 increases by 1 standard deviation, then y hat changes by b1 hat, so this coefficient, standard deviations. So now it's about standard deviation changes in all the independent variables that are standardized, or we've taken the beta coefficients of them, or we're calculating the beta coefficients for them. So now it's a 1 standard deviation in these independent variables, and we're interpreting the parameters on them as how much they'll cause the standard deviation of y to change. So that's how we're thinking about interpretations in general with these beta coefficients. But let's kind of erase this. We'll write out a regression, a theoretical one with a specific example, talk about how we interpret theoretically, and we'll kind of come up with some numbers for these actual estimates for beta coefficients in that example and talk about what they mean. So let's say we're interested in kind of the effects of pollution on housing prices, and we're going to look at kind of nitrous oxide in this example, and that's going to be measured in like parts per million, which you might not be familiar with, and so it might be hard to interpret what a change of 1 would be. So let's think about, let's write out our regression, think about how we'd interpret it with the coefficients we did before, and then let's apply beta coefficients and think about how we'd interpret them afterwards. So I'm going to put before, and what I mean is no beta coefficients. So just the regular regressions that we're used to so far in the course. And let's say we think that the price of a house is going to be a function, or we're going to run this regression, beta 0, our intercept, beta 1, NOx, and this is going to be the nitrous oxide in parts per million, and I'll kind of label it somewhere. Maybe the crime rate influences the price of a house, and we can have some hedonic pricing here, so number of rooms in a house, maybe the distance to an incinerator or to a community center, and then maybe school characteristics matter too, because it's in a certain catchment area and people know that sending their kids to good schools is really good, so they're willing to pay kind of a premium. It's worth more, and so we're going to call it student-teacher ratio is going to be the other variable. So let's say this is our regression that we're interested in. So here, let's say our variable of interest is NOx, which is nitrous oxide, which is kind of measured in something we might not be familiar with, or we think might be, as an economist, I might think this is a weird scale. It's measured in parts per million. Might not be familiar with this. Okay, so this is the regression we're interested in. We're particularly interested in this variable. And so how we'd interpret this before, if we just use our normal coefficients, we're not using beta coefficients yet, would be an increase in 1 part per million causes housing prices or causes a beta 1 change in the price of a house. So this is like the population one, right? It's not an estimate, so we can just say it's causing that. It's the real effect. Okay, so this is how we'd interpret it before. But now let's think about what our regression looks like now, and hopefully we have enough room to fit in the interpretation. So let's write with beta coefficients here. So now we're going to use beta coefficients. I think I did the other thing in blue, so let's continue that. So I'm just going to write price out again, but now this is the z-score. Maybe I should put z-price to make it more obvious that it's the z. That's the transformed variable. Z-price equals B1, assuming that we're standardizing all the variables, there'll be no intercept. B1 times nitrous oxide, or I should say the z-score again, I should kind of correct myself here. Z nitrous oxide plus B2 Z crime, if we standardize the crime variable too, plus B3 Z rooms plus B4 Z distance, and so on and so forth, plus B5 Z STR, and then we just have some new error term here. And again, let's say the variable we're interested in is this nitrous oxide. So now what the interpretation of this coefficient or this parameter on nitrous oxide would be is a 1 standard deviation increase in nitrous oxide in the atmosphere causes a B1 standard deviation change in the price of a house. So now, again, it's about standard deviation changes once we take the beta coefficients. Once we apply this transformation to our regression, instead of that's just going to be an option on the end of a regression, it's going to be like comma beta or something like that, I think it is. So it will automatically transform your variables, and your output, you can interpret it in terms of these standard deviations. So 1 standard deviation increase in nitrous oxide causes a B1 standard deviation change in the price of a house. So I'm going to erase this quickly and we'll do actual, let's say we actually ran this regression in data and got these different coefficients and what they mean particularly. So let's say we actually estimated that, that last example, and we've estimated it using beta coefficients, and we get the following results. So let's put a z hat price here to say that we ran the regression. And we get the following results. We get minus 0.340 times the z-score of nitrous oxide, minus 0.143 Z crime. What else do we have? Plus 0.514 times the Z-score of rooms. minus 2.35 times the distance coefficient here, the z-score of the distance. And finally, we have the test score. Let's say it's plus 0.222 times the z-score of the student-teacher ratio. Hey, maybe some of these signs might not make sense. I think they mostly do. But we're just kind of using it to interpret the second one. So let's say we actually ran this regression, we get minus 0.34 as our beta coefficient on the variable that we're interested, which is nitrous oxide. And so what this is saying now is interpretation. A 1 standard deviation increase in nitrous oxide, NOx is what I'm trying to write here, in nitrous oxide is predicted or estimated to decrease housing prices by 0.34 standard deviations. So that's how we'd interpret an actual estimate if we ran this in Stata. Now, a lot of times you don't have to standardize all the independent variables, or we don't have to standardize the dependent variable. We can just choose which ones you want to standardize, especially if they're kind of on that strange scale. That's the ones we want to kind of transform. So we want to transform a test score if it's out of some weird number. So that's how we interpret beta coefficients.